We see the regular increase of distance from the sun as we move out. Each planet's distance increases by a factor of 1.5 or 2 compared to the previous planet's distance. One little exception to that actually is when we jump from Mars to Jupiter. It's a larger jump, around a factor of 3, because we're skipping over that asteroid belt zone. But anyway, most of the planet's orbits are pretty circular with very low eccentricities. They're all pretty much in the same plane. So let's look at what would a successful model for the formation of the solar system have to be able to explain. Now, first of all, when I talk about a successful model, what I mean is we're talking about like a physical explanation, starting with some kind of starting point, to take us from that starting point to what we see now in the solar system over the span of 4.5 billion years. That's what you mean by a model, a physical explanation for that evolution that took place from this initial state to what we see now. Okay, so whatever that model turns out to be, it has to be able to explain the planets all orbiting the same direction, spinning pretty much in the same direction, although there's a couple of exceptions to that, as we've seen. Most of the moons of planets orbit in the same direction as the planets themselves spin. We see the differentiation. We see asteroids being different in structure from planets, and we'd like to know why the comets are primarily in the Oort cloud. So there's a bunch of things. That's actually a pretty short list. We could add a lot of things to that, but I'm trying to be brief here. All right, so let's talk about models for the formation of the solar system now. We think that, again, the process of formation started around 4.6 billion years ago from a large cloud of gas that was hanging around in the galaxy, which was also in the process of forming around the same time from an even larger cloud of gas. So the idea was that perhaps you could have a cloud of gas in our galaxy, which is a very large cloud of gas, maybe a light year across. That's like 1 trillion miles across. Now, a cloud like that is going to have its own self-gravity. Every molecule or atom in that gas is going to attract every other molecule or atom in that gas, and that's going to tend to pull them together. Now, each of your bodies in this room is actually exerting a gravitational attraction on everybody else's bodies in this room, right? But you don't all fall together because there's overriding forces here, like you're sitting in your chair, and the frictional force of you sitting in your chair is much stronger than this gravitational force of pulling you together. But when we're talking about this cloud, 4.6 billion years ago, there wasn't any other force. It was just gravity. It's hanging around in space, floating in space. Even though that gravitational force is small, it's going to tend to cause the cloud to collapse. So the first person to really think about how we could build a physical model for this process was good old Laplace in 1796, one of the early mathematical physicists. So we start with a dark cloud, perhaps a molecular cloud, and we have this model we call the nebular model. It starts with a nebula, which is a cloud. Okay? It's a fancy word for a cloud. Probably, as I say, about a light year across, starts to collapse because of its own self-gravity. Now, everything in the universe spins to a certain extent. There's no such thing as an object that doesn't spin. It's almost impossible. So this cloud actually would have had a little bit of spin to it because everything has some spin in the universe. Well, as this cloud collapses and shrinks, it's going to go from spinning slowly with a slow period that probably was like maybe as long as 100 million years or so. It's going to start spinning faster with a shorter period. And this is just the same phenomenon, of course, as the skater pulling in his or her arms. And actually what it is you're creating a smaller moment of inertia. That causes you to speed up because you have to keep the same amount of angular momentum. That's angular momentum conservation. So as the cloud shrank, it had to spin faster so as to still have the same amount of angular momentum. Okay? So what we end up with is a cloud that's shrinking and spinning faster and faster, and then eventually, when it's gone from about a light year, and remember a light year is like 100,000 astronomical units, okay? When it's gone down to about 100 astronomical units across, which is about twice the size of our solar system right now, it's shrunk by a factor of about 1,000 or so, right? So when it hits 100 astronomical units, it's 1,000 times smaller than it was in the top picture right there. There's been a tremendous amount of shrinkage. So what happens is that the centrifugal force that develops from the rapid spin tends to keep it extended in the direction perpendicular to the spin axis, because the centripetal force, when you spin a rock on a string, it spins in a plane because you have centripetal force, right? Well, the spinning cloud has that centripetal force, but in the direction along the axis of spin, there's no such force, so it just collapses that way. So we go from a sphere, roughly spherical shaped cloud, to a pancake-shaped cloud because of this spinning effect that only occurs in that one plane, not perpendicular to it. So in the vertical direction, it just flattens right out, but it's able to resist that in the horizontal direction because of the centripetal force. But it's shrunk, again, by about a factor of 1,000. So we go from large radius slow rotation to small radius rapid rotation. That's the effect that we're talking about right now. Nebular model, we continue. We're not done yet because we don't have planets. All we have is a spinning disk, a spinning pancake. It's actually conceptually the basis for the earliest ideas for the ion. It was a single gigantic pancake. Now that they modified that, because it wasn't a very good business model. But what we're going to do now is talk about how we go from this pancake shape to actually having some planets. So we have the sun forming at the center of this disk. And Laplace's idea, remember this is all Laplace's nebular model we're talking about right now, his idea was that the material would tend to form into rings. He didn't have a really good explanation for why that would happen, but that was what he thought would happen. And then the material in the rings coalesces and sweeps together, and you end up with planets. Okay? But there's a problem, just as I say here. The problem is that the collapse that needs to take place to form the planets actually isn't going to occur in the nebular model, because when things collapse, they tend to heat up. Remember, we learned that in the case of Jupiter. Jupiter's emitting twice as much energy as it receives from the sun, because it still has this energy of the gravitational squeezing that's leaking out, right? So Laplace's idea actually wouldn't work, because when the blobs, the rings, try to condense to form planets, they heat up. And when something heats up, its pressure goes up too. And that pressure resists the collapse. So you don't actually collapse to form planets. Instead, the pressure is high enough that everything is going to stay pretty much diffuse and spread out. And that's basically because the matter is warm. Warm matter is going to have higher pressure. So that doesn't really work. So now we move on to another model in the 1800s called the condensation model. Condensation theory. It's just a slight tweak, not twerk, but tweak of the nebular model. Okay? So what we do is we take the nebular model. We're going to start off with exactly the same idea of the large cloud, and it spins and it collapses. All that stuff's the same. The difference is when we start talking about the formation of planets. Okay, here we bifurcate away from the nebular model, and we add a very innocuous thing. You wouldn't think it would make that much of a difference, but dust. If we suppose that there's dust particles sprinkled in with the gas, that makes a world of difference in terms of the ability to form planets. Because the gas, the dust particles are actually going to attain a certain temperature because of the sunlight that's hitting them. That temperature is probably going to be pretty low, probably only going to be a few hundred kelvins or so. And those little dust particles, when they reach that temperature, they're going to radiate away energy themselves. But the energy that they radiate away is going to be infrared radiation. And infrared radiation is able to escape from the cloud. So what this means is, because you've got the dust in there, you're taking some of the sunlight, which sunlight would normally keep the gas warm, but you're converting it basically to infrared through being absorbed, and then the energy is re-emitted by these little tiny dust particles. And so the yellow sunlight shining on the gas cloud is re-radiated as infrared, and the infrared escapes from the cloud. Hence, you're cooling the cloud down now. That would not have happened if you didn't have the dust particles. Because without the dust particles, you have sunlight coming in, being absorbed by atoms, and sunlight coming out. Remember, atoms emit exactly what they absorb, right? So if an atom absorbs yellow light, it's going to emit yellow light. You haven't really done anything to cool the gas because the sunlight can't get out of the cloud. It's locked into the cloud. So the dust changes that completely by converting some energy in infrared, which is able to escape. Okay, so what this means is that we're able to cool the cloud, we're able to reduce the pressure, and dust also does a second thing for us. Dust particles can act as condensation nuclei, much as in a rain cloud forming raindrops, right? You don't get rain if you don't have condensation nuclei in your rain cloud. And sometimes you can actually seed a cloud using an aircraft spraying out little bits of dust and actually forming cometary nuclei so you can get it to rain. Same idea here. So the dust acts as condensation nuclei, helping the atoms of the gas to stick together, accelerating the process of formation of larger and larger blobs, which can then form planets. So those are the two key effects that we get from dust. We get the ability to cool the cloud, and we get the condensation nuclei effect. And so we have now the condensation theory. And by the way, we don't even form rings, which again, Laplace didn't really have a very good explanation for. But there are no rings in the condensation theory. It's a smoother type of process. So here, these little squiggly lines just indicate that the dust is radiating away infrared, and that helps to cool. Okay, so now we have a new sequence here. It's a little different from the nebular sequence of snapshots. We start with the disk at the top, which is pretty hot with the primordial sun forming in the center. Then we get the dust, which starts to cool the nebula by emitting infrared radiation, reduces the pressure, and we start to get protoplanetary blobs forming, which are basically a kind of a agglomeration of lots of little dust particles that are accumulating gas atoms on their surfaces. And through a process we call accretion, smaller things get stuck to larger things, and essentially all the material in the gas is swept up. And in the condensation theory, we don't form rings, but we do form planets this way. So the formation of planets takes place by this process I call accretion. Small objects sticking together to form larger blobs. And at a certain point, there were millions of these objects we call proto-planetesimals that were probably around the size of Pluto. In fact, these planetesimals I'm talking about now are really very much like the Kuiper Belt objects that we see now, which actually are the short period comets. So when we look at the short period comets out in the Kuiper Belt, we're actually seeing probably a cross-section of those early planetesimals that formed way back when and managed to survive without getting involved in the accumulation to form larger and larger bodies. So that's why they're so primordial. Okay, so the planetesimals I'm speaking of now, there were millions of them. They're pretty small, and they would have had pretty chaotic orbits, pretty eccentric orbits. But as they accumulated together, their eccentricities kind of canceled out, leaving us with planets that have pretty circular orbits. The leftover material, says there, would have formed the Oort cloud and would have been also left over in the Kuiper Belt. And we also had some asteroid material left as well.